Get started here. Chapter 1 seems like a good place to start. Why not? All right, so in chapter 1, we're going to talk about chemical foundations. We're really going to start, like I mentioned before, our textbook is sort of arranged differently than sort of a normal, I guess, regular chemistry textbook. So we do start, as the title implies, with atoms first. And that means really in this chapter, we're going to get into the atom. We're going to get into, again, some of the important experiments that helped us understand the structure of the atom. We were towards the end of the chapter, get into things like figuring out how many protons, electrons, neutrons, mass number, atomic number, and those type of things. And then, like I said, in the next chapter, we get right into like electron configuration and stuff like that. So remember, again, as we talked about last time, they sort of expect, in a sense, that you know certain things coming in from Chem 100 and things that are in like a traditional sort of arranged chemistry textbook, like significant figures, conversions, and all that type of stuff is actually like a review chapter in this particular book. So again, it's in there if you need it to review it and stuff like that. And again, it should be the chapter that comes right before chapter 1 there. As I also mentioned, right around when we do study assignment A, which is pretty much on all those topics of significant figures, conversions, and things of that nature, we will have kind of like a formal-ish lecture on all those topics. Again, just to make sure everybody's on the same page, and we'll probably do that little lecture there in lab on that day when we kind of have study assignment A sort of schedule. So let's get into it. So chemistry is really, for the most part, the sort of study of matter and sort of how it changes. As you may be familiar with, matter is pretty much anything that occupies space and has mass. So that's pretty much, anything. And what we really try to look at a lot in chemistry is, try to explain sort of on the microscopic world what's going on things that we sort of see, we just kind of observe on the big scale there. And so we try to figure those things out. So a lot of chemistry is involving those different states of matter. Thank you very much. And also really how those states of matter and changes, or how matter changes from one state to the next, the sort of energy involved in that. Chemistry is obviously in all parts of our life, obviously just regular chemistry, things like food chemistry, obviously cosmetics, medicine, right? Forensic science, so it's a field that crosses over into a lot of different sort of genres. And when we talk about matter, there's usually the 3 states of matter that we should be familiar with, which is solid. And again, in the solid state of matter, everybody is packed in there really tight to one another. Again, that is why it is pretty much solid. They all kind of lock in tight to one another. They're usually very rigid. They're very hard to change the shape of it. We also have our liquid state. In our liquid state, things again are still relatively close to one another, but sort of a majority or a major difference between, say, the solid state and the liquid state is in the liquid state, they actually have a little bit more energy. And what that allows them to do is, although they're still kind of near each other, they're able to actually kind of move past one another. So they're able to kind of pass each other and move around in that liquid state. That's why when we think about liquids, they are fluid, right? So they're able to kind of pour in like that. They have a little bit more energy, a little bit more movement sort of happening. And then we have our gas state. And in our gas state, that is the state where everybody is basically broken apart from one another. They're flying around. And as they're causing collisions, as we'll talk about in the gas chapter when we get there, obviously that's what we associate pressure with, right? So when we think about gases under pressure, gases causing pressure as they're flying around with a lot more energy, obviously, because they have freed themselves from each other and they're flying around. There's a lot of collisions that occur. And again, that's sort of directly related, obviously, to the energy that's going on. So when we talk about states of matter, these are the 3 main states of matter. Again, a lot of what we look at in chemistry is how these guys change, right? So When we go from the process of solid to liquid, that's process of melting, right? Like we take an ice cube out. And if you go from liquid to solid, that is freezing. Yeah, that's good. If we go from liquid to gas, that is the process of evaporation or vaporization. And gas back to liquid is condensation. We could also go from solid directly to the gas, skipping the liquid phase altogether. That is what is known as sublimation. That's like dry ice. If you ever use dry ice, seen dry ice, right? Solid, very cold, by the way, but solid, and then it goes directly into the gas phase. No liquid cleanup along the way there. Dry ice, by the way, is actually carbon dioxide. It's not water. And there's also gas where we skip the liquid and we can go back to a solid. That's what's known as deposition. Like you're depositing something onto something. If you have seen DVDs or CDs and they're really, really shiny, that's sort of the process they do use. They use deposition to sort of deposit some metals on it, gets it really, really shiny, those sort of discs. So a lot of what we also deal with in chemistry is these sort of phase changes and changes of state that occur. So for example, here, when we talk about melting and freezing, does that occur at the different temperatures or the same temperatures? It actually occurs at the same temperature. And for example, water, which is a good one to know, water's normal freezing point is 0 degrees Celsius. And when we talk about sort of water, for example, at 0 degrees Celsius, exactly 0 degrees Celsius, you actually have both phases happening at the same time. You have kind of like a little bit of ice, you got a little bit of water, kind of like ice crystals happening exactly at 0 degrees Celsius. It's not until you get a little bit above 0 degrees Celsius that you sort of transition into liquid water, not until a little below 0 degrees Celsius that you truly transition into really solid ice in that particular case. What determines what happens is really the energy component at 0 degrees. So it depends on what you're doing in terms of energy as to sort of which way you'll go. Will you make liquid or will you make ice? And that's really the energy component. Same thing over here, evaporation, vaporization, condensation also happens at the same temperature. And for example, that's what's known usually as the normal boiling point of a substance. And the normal boiling point for water is 100 degrees Celsius. So that is the normal sort of boiling point that we have here. Now, speaking of that, energy is also a really big part of what we look at in a lot of chemistry. With that being said, except for in this class where we don't look at it all that closely because it's moved to Chem 1 200B there. But we will, again, as I mentioned the other day, we will obviously mention some energy. We'll talk about energy because, again, the book kind of thinks you do that chapter and don't skip it in this class. So we will talk about energy, but a lot of what we do look at does involve energy. So when we go from, say, solid to liquid to gas, does that involve energy being put in, or is energy being released when you do those processes? As we go in all that process. So if we started as solid, then I wanted to make, say, liquid water, and then I wanted to make, say, gas water, doesn't sound right. Water in the gas stage, energy needs to be put into it. Yeah, so this is all processes where energy is absorbed. So if you think about it, and those processes, by the way, when energy is absorbed are what are known as endothermic. Out of room there, so I'll go over here. So that is endothermic. All those processes. And if you think about it, when we take out an ice cube, for example, and one really good way to sort of think about heat and energy and how heat flows from cold to hot or hot to cold? It does go from hot to cold. So heat does flow from hot to cold. So when you take out your ice cube, it's obviously colder than the room temperature air. So the room temperature's air heat flows into your ice cube, which is why if it just sits there, right, it just starts to melt without you doing anything because it's picking up all that warmer air from the surroundings. Obviously, if you're going to make some pasta for dinner, right, you take some liquid water, you throw it up there on the stove, and you put some fire under it, or electric heat coming out from under it, depending on what type of stove you got going on. And that's going to absorb a lot of energy and heat in that sense. And that turns it into your water starting to boil. And that produces steam, right? And steam is really still water, right? In the gas phase is what steam is. It hasn't changed into anything new in that case. So those are all processes which are known in general in chemistry. Whenever there's sort of energy being absorbed, that is what is referred to as an endothermic sort of process. Obviously, if we're heading in the opposite direction there from, say, gas to liquid to solid, those are, again, all processes where actually energy has to be released. So the opposite there, energy needs to be released. And that is what is known in chemistry as an exothermic process. The idea here is if you think about gas molecules, they have a lot of energy. They're flying around really fast, which means when they release their energy, they're actually going to be flying around a lot slower. So when they come in contact with each other, they no longer have enough energy to kind of escape each other. So they kind of clump and fall into like the liquid phase, if you will. And if you continue to remove energy, they will then really kind of slow way down and obviously lock into sort of the solid phase at that particular case. That is actually what happens when you put your liquid water in the freezer, right, to kind of make ice. Although it may not seem that way, but that is what's happening because when you put your liquid water into the freezer, at that point, your liquid water is actually hotter than the air in the freezer. And that's going to draw out all the heat and energy from the liquid water, going to slow down your liquid water, and now you have ice cubes, right? And it's going to go into the solid state in that particular case. So again, a lot of what we deal with in chemistry does involve matter. It involves how it changes in chemical reactions, the energy component of it, and what's happening in terms of energy along the way. Again, in terms of endothermic and exothermic, as we'll talk about perhaps in the next chapter a little bit more, when we calculate sort of energy values, for example, and if we calculate any type of energy values, which you may be familiar with Q, like you did maybe with specific heat capacity, and Q is heat or energy. Delta H, which is the change in enthalpy. And that's a general sort of value that we calculate a lot in chemistry, which is kind of like the heat of the reaction. What's going on overall in that reaction? Is it giving off energy or is it sort of absorbing energy? So if typically speaking, you have an exothermic process that gives out energy or releases energy, when you calculate any type of energy sort of value, those guys are usually negative values. So delta H's are negatives, Q's are negative type values. And that implies that that energy is overall being released in that process of whatever you may be looking at. Endothermic is opposite. When you calculate energy for endothermic processes, you will get a positive number. Same thing for delta H, and Q will also be positive numbers. So these are things to look at because, again, they do assume that you did look at the energy chapter there as you go through the book. And a very, very common way when we see something like a chemical reaction, the very common thing that we see in terms of knowing whether or not it is a exothermic or endothermic type process is they oftentimes will just give you the delta H value for it. And they'll give it as either a positive or negative value. And from that value that they give you, you will be able to determine, whether or not that process there is going to be sort of exothermic or endothermic. Any questions on any of that stuff there? All right. So let's talk a little about matter. The sort of simplest representation, for example, of all elements are atoms. And as we'll talk about in this chapter, atoms are basically made up of protons, electrons, and neutrons. And the atom is really the smallest element that can enter into chemical combination. A molecule is two or more atoms joined together. So there are a couple of sort of terminology that sometimes confuses people. So when we talk about elements, elements are really like the basic units of them are atoms. And they're really like the sort of building blocks of everything. Obviously, we have a periodic table of all the elements that we got going on. You could think of elements kind of like the alphabet, and just like the alphabet, right? You could do different combinations of letters, you can make different words and stuff like that. Obviously, different combinations of elements will oftentimes create different compounds along the way, different molecules. And that's sort of as far back as you could go. So, for example, if you wanted to break apart something, as far back as you could go is pretty much to the elements. You can't go any further than that. You could break down most things into their elements. A molecule, as you can see here in this definition, is a definition of basically you just need two or more atoms that are basically together. Now, there are certain elements that they come as diatomic molecules, which means di is two, atomic is atom, so they come as two atoms together, and that is how they naturally come. So there are certain diatomic molecules which are elements, and those are things like hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine. Uh, maybe you can see it. Iodine, maybe you can see that through there. I guess, yeah. So iodine as well. So that is the way that these particular elements come. They come basically as twos. You have two hydrogens, you got some double bonded oxygens coming as twos, got a triple bonded nitrogen happening. And if you had any of these guys by themselves uncombined, that is how they will basically come. Most all other elements that you see on the periodic table will essentially come as what is referred to as being monoatomic, which means they come as ones, basically. By the way, do things on the periodic table by themselves, uncombined, do they have charges? The answer is no. So any element that is by itself does not have charges. Things only get charges, as you might remember, when they go hook up with somebody, particularly nonmetals, metals and nonmetals coming together. And that is when we form things that are called ions that do have charges. But if you had a piece of copper metal by itself, it has no charge. It's neutral in that sense. Again, things only do gain charges when they kind of hook up with other people. So we do have elements that are diatomic molecules, and there's two sort of words that sometimes people get confused or not necessarily sure sort of what the difference is, between those two things. And one is molecules, the other is a compound. And a compound is the combination of two or more different atoms of different elements. So, in order for something to be a compound, you have to at least have two or more atoms involved, but you also need to have at least two or more elements involved as well. So, that's different than a molecule where it's kind of like a generic, general definition of all you have to have for it to be a molecule is two or more atoms. They could be two or more atoms of the same element. They could be two or more atoms of different elements. But the basic definition of this thing as a molecule is all you need is two or more atoms. Now, a compound, there is the added part to that, that in order for it to be a compound, you do need two or more atoms of different elements. Yes, sir. You can use either one. I'm gonna answer this, I guess, this way. There's probably no context where you'll have to kind of choose that in a sense. In most cases, you do need to know the difference between what they two are. Yeah. So and So to maybe better answer that question, let's take a look at a couple of examples and sort of explain a couple of things. So for example, we have oxygen and hydrogen, and how oxygen and hydrogen come, which are these guys here. These guys here, like oxygen or hydrogen, these guys are molecules, obviously, because they come as two atoms together, right? Two or more atoms, so they meet that definition. These guys are also elements because, frankly, there is no other element atom involved there. They are not compounds, right? Because when we look at oxygen, it's just two O's, right? Two oxygens, two hydrogens, no other elements involved. Now, if we look at water, when they do come together and make water, which, if I remember correctly, looks something like that, I think. When we look at this, this is also a molecule, right? Because it does have two or more atoms involved. And it is also considered a compound because it has two or more atoms and two or more elements involved in here as well. So they're both. So you could refer to water as a compound. You could refer to water as a molecule. Most of the time, probably if you were to refer to water, you would refer to it just by its name of water and stuff like that in most cases. Yeah. Water obviously is not an element, right? Because obviously we have atoms of hydrogen and we have atoms of oxygen. So that's not good for it just being an element. It has to be obviously atoms of the same element for it to be an element. Any questions on the differences there? All right. So as I kind of showed there before, when we do write sort of formulas, we do use the subscript. When we do write just chemical formulas in general in chemistry, and again, the subscript tells us how many atoms we have of each of those guys. The subscript always goes to the guide to the left of it, right? So that is always what that represents. So in this case, for water, we would have two atoms of hydrogen. Pretty much in all chemistry applications, if you do not see a number there, like my circle next to the oxygen, it is assumed to be one. So typically speaking in chemistry, we don't really put one on most things that we write as formulas. We oftentimes don't put ones when we're balancing equations or anything like that. So if you don't see anything there, it does represent one basically. And that also obviously goes to the guy to the left there, and that would be one atom of oxygen. So when we see those subscripts, as we'll talk about in a later chapter as well, they also represent how many moles of each of those elements that you got going on. So you always want to make sure you write sort of formulas correctly. Now, the other major thing, obviously, that we look at, obviously, here in chemistry are chemical reactions. And that's part of how things change when we have a chemical reaction that occurs. When we look at the chemical equation, there's really two parts to it. There is the reactants, which is on the left-hand side of the arrow. That's your starting material. And really what it forms, which is what sort of the arrow represents, are the products. So this is what is really sort of made as a result of a chemical reaction. Now, as we'll talk about a little bit as we get through some of these chapters, but all chemical reactions really only involve pretty much breaking bonds. And then you make bonds. So really, as we'll also get into some of the chapter, it really only involves electrons. So electrons make up the bonds. They're really the only thing that it gets sort of changed in a sense, or is sort of broken and used in a normal chemical reaction. That is also why we balance equations in chemical reactions, because we have the conservation of mass. We don't lose any elements along the way because the only thing involved in a chemical reaction are electrons. And that means that we do conserve elements as we go from reactants to products. The only thing that happens is we break apart all the reactant bonds, and then they kind of reassemble and make new bonds on the other side. So if you start with 4 carbons, you'll end with 4 carbons. They will just be perhaps in different compounds or molecules on the other side of the arrow. And that is, again, always reactants to products. We can break apart compounds back into their elements by some type of chemical change. Chemical change is something that occurs where what you start with and what you end with are two fundamentally different things. So, for example, if you take water and run an electrical current through it, you will break apart the water from its molecule or compound back to its elements here. And once again, once you hit the elements, that is as far back as you could go. Some schools do that experiment. All you need is a 9-volt battery, a little acidic water, and some leads, and you can break apart water as well, basically. So, again, we can break this back through chemical means. We can't do it through physical means. And we know that it doesn't really happen through physical means. Physical means are things like boiling, filtering, freezing. And we could go back to our example of making pasta water. It would be a very different event if you broke apart your water when you heated it to its boiling point. You would produce hydrogen gas and oxygen gas, and perhaps you probably wouldn't get to the pasta part of the program at that point if that's what you produce. So we don't do that. What is happening when we do boil water is it's actually a physical change occurring. We're taking it from liquid water to steam, which is water in the gas phase. That's all those bubbles that you see as it starts to bubble, right? What's inside those bubbles? That's water vapor inside those bubbles. That's basically water in the gas form. They sometimes don't make it to the surface because the pressure inside the bubble is less than the pressure outside. So they pop before they actually get to the surface. That's why you really don't have boiling water, right? Until it's really raging boiling, right? They get to the surface. At that point, they do pop, right? You might even wonder why when you hit it right at the very first, if you've ever looked at water and you like hit it really quickly with the fire, and all of a sudden you see all these little things that look like bubbles and stuff like that. And sometimes people think, oh, that's kind of a quick thing. It's starting to boil right now. But it's really not. What's actually happening in that case is you're changing the temperature and the solubility of something like carbon dioxide changes and it's less soluble. So you're just seeing that coming out of your actual water right at the very beginning when you hit it with the gas. It's really not till you see those really good bubbles, right? That is truly boiling, because clearly you can put your finger in there. You should never do that while you're boiling water, but you can feel it's still cold right away when you hit it, and even though you might see bubbles happening in that particular case. Any questions on that there? All right. So also a very big part of sort of science and chemistry is the scientific method. And really sort of the scientific method is used to really explore sort of observations that you make. So really sort of the beginning part of the scientific method is you make some type of observation or somebody makes some type of observation, and maybe you work for somebody and go in an academic lab and go, hey, I observed this, or somebody you work for observes something and they go, why don't you try to figure out what's going on with that, right? Why is that happening? So we try to come up with a testable, tentative explanation of why what we're observing is happening. And usually a good sort of hypothesis is one that can be tested through some type of experimentation that you can sort of try to figure out what is actually happening. So a nice testable hypothesis allows you then to sort of do some type of experiment to explore sort of what is going on. And the good news about the experiment is, and the bad news is, oftentimes experiments lead to a big U-turn of more observations. Maybe you get lucky and you observe something of what you thought you might see, but a lot of times you might observe a lot of other things. And that leads to perhaps you need to revise your hypothesis, come up with a new hypothesis, and that's going to lead obviously to more experimentation. It can become sort of a vicious loop, also known as your graduate research and until you're done and graduate for college. But hopefully what comes out of it is at some point, one of two things sort of you see, either a theory or a law. So those are kind of two things that hopefully will sort of come out of all this. Now, there is sort of a difference there between a theory and a law. And sort of the way you could kind of think about it, for example, is a theory is an attempt to explain why things happen. So a theory is a model. Perhaps you do some experimentation. Perhaps you come up with some ideas as to, you know, what is going on in your particular situation. The idea with a theory is it's not really locked into cement. You know, it can be found through further sort of experimentation that maybe parts of your theory is not so great anymore. Or maybe parts of your theory is good, but other parts are bad, or maybe the whole thing is pretty bad along the way. So, for example, the Dalton's atomic theory. For example, one of the things that he said in the Dalton's atomic theory was that the atoms of all of the same element are identical to each other. So all atoms of the same elements are perfectly identical to each other. And later experiments, because he didn't know about things called isotopes, which we'll talk about shortly in this chapter, that exist, which are the same element, but they actually have different numbers of neutrons, which means they are not identical to each other, but they are still the same element. Something like Bohr's model of the atom as well, or Bohr's theory of the hydrogen atom, is a model that works really, really well for hydrogen or anything else that has just one electron. But once you move off to things with more than one electron, it doesn't really sort of hold up very well. So theories you can think of are tentative sort of models. They're not necessarily set in stone. They can be found later on to be semi-right, some things not so right about it. Now, a law, on the other hand, is something that is pretty much going to always summarize what's going to happen in that situation. There's kind of like no wiggle room on that. It's sort of locked in. It should always happen that way. As we talked about earlier, sort of like the law of conservation of mass. And the idea there in a chemical reaction, like I mentioned a second ago, if you started with 4 carbons on your reactants and you're going to end with 4 carbons, and because carbon weighs about 12 grams per, you'll have the same mass on both sides. Again, those carbons may be in different things on both sides, but if you add up all the masses of the elements on both sides of your equation, you will end up with the same mass on both sides because we have the same elements being conserved along the way. Same thing with the, say, law of conservation of energy. Energy is not created nor destroyed, but can definitely transform from one place to the next. So a lot of times when we think about energy, we think about it as sort of moving from one place to the next, the energy. We think about systems, surroundings, and how it sort of moves. You know, for example, the classic example of energy, which is the giant boulder on top of the hill there, it's got a certain amount of potential energy based on its position, right? And if it kind of goes over the hill, it will then turn some of that potential energy into kinetic energy, right? Which is the energy in motion until it, you know, perhaps hits the ground. Hopefully nobody's underneath there, which clearly it will transfer some of that energy to the ground. But if you added up all the energy through that whole process, you know, you'll have the same energy you sort of started with. It just maybe moved and transferred from one place to the next. So those are things that always occur when we think about sort of energy and those type of laws. Questions on that there? All right, so talking about that, we're now going to sort of talk about really the atom. We're going to lead into some experiments that helped us understand sort of certain parts of the atom. As we go through it, I'll kind of mention, you know, what things you need to know in terms of people and experiments and stuff like that. So atoms all sorted sort of a long time ago, obviously with the idea of Greeks first trying to explain what's going on in terms of chemical changes and chemical reactions. Our friend Robert Boyle there was considered the first chemist. There's sort of, as I mentioned, speaking of laws, 3 sort of important laws, you know, which again are how things always sort of occur. Again, as we just mentioned, the law of conservation of mass. Mass is neither created nor destroyed.
Chemistry demonstration. This is going to be law of conservation of mass, or law of conservation of matter, depending on which way you like to talk about it. So the law basically says that in any chemical reaction, matter or mass is conserved. It cannot be created or destroyed. That means that when you start a chemical reaction, the mass before and the mass after should be the same. I've got some calcium chloride here, which I'm going to use to place in the Erlenmeyer flask. Exact amounts are not necessary in this demonstration, So that's probably about enough. Place that on my balance here. In order to have a chemical reaction, we need two chemicals. So I am also going to add some sodium sulfate. I'm going to add it in this test tube. About half full should be good enough. So I'm going to place the test tube inside the Erlenmeyer flask. Notice that the two chemicals are not mixing yet. I'm also going to use a stopper to stop up the top of the Erlenmeyer. And we are now going to note the current mass on the balance. You should be able to read that. It says 369.1 grams.
So obviously these are our reactants.
To get this reaction to occur, I placed the stopper on the flask. That way, if there's any gases created, it won't allow them to get out. Also, in order to get this, in order to get these two solutions to actually mix, I have to flip it upside down. So I'm going to flip it upside down, carefully agitate the two mixtures. The two solutions actually mix, and you can see there's a pretty startling reaction here. When I place this back on the balance, what you're going to notice is that it's the same mass as before, plus or minus a decimal.
Okay, so as we can see there in that video, again, obviously as we were talking about, we don't lose any sort of elements along the way in a chemical reaction. Again, the mass really of all of our reactions is going to be the same mass as what we have on our product side. Now, our law of definite proportions is another one. A given compound always contains the exact same proportion of elements by mass. Things like water is always 2 hydrogens and 1 oxygen. And again, you can figure out how many grams, for example, of oxygen there is per hydrogen or hydrogen per oxygen. And also the idea of law of multiple proportions that says when two elements from a series of compounds, the ratio of the masses of one of them to the second will always be reduced by a whole number. So for example, here, if we take something like CO, which is carbon monoxide, CO2, for example, which is carbon dioxide. Carbon is about 1201 and oxygen is 16. So it's like 2801, its molar mass. And we have carbon on the other side there, 1201, and a couple of oxygens. So its sort of molar mass is 4401 in this particular case. So if we take how much mass of our oxygen grams to carbon grams, that's for the carbon dioxide, that is, we got 16 divided by 12.01. That gives us a ratio there of 1.33. We do it for our CO2, grams of oxygen per grams of carbon. In this case, our oxygen is 32, 12.01 for our 1 gram of carbon gives us a ratio of 2.66, right? The relationship between these two ratios is a factor of 2, right? So we could see there's twice as much oxygen, right, as we do have carbon in the first one. So again, that's the idea there. Things will always, in a sense, sort of be found in terms of atoms. They will always be sort of whole number sort of multiples. We never really have like a half of atom or anything like that. Things will combine in those sort of ratios. Any questions on that combination there? Yeah, our calculation. All right. All right, so let's talk about some of the early ideas of Dalton and really the atom. And a lot of it did start with Dalton. And John Dalton was not a great lecturer. He did like math. He would record the weather every day. He'd wake up, record the weather. Oddly, did not get married, but did like to go bowling on Thursdays, which if you learn nothing else in this class, that is what you should know. Will be on every exam. Don't miss it. It is not like discount Saturdays or, Cosmic Fridays. It is Thursday. But really, besides going bowling on Thursday, what he's known for, he did formulate sort of Dalton's atomic theory, which sort of tried to explain what's going on with atoms. And let's take a look at some of the main parts here for Dalton's atomic theory. The idea here is he said that each element is made up of these tiny particles, which are atoms. He also said that atoms of a given element are identical. So as I mentioned a second ago, that is one of the parts really of Dalton's atomic theory that is really not sort of correct anymore. Again, the presence of isotopes sort of disproves that. So that part of it is really not correct. And you do need to know, obviously, that part that's not correct. You also do need to know the different parts, obviously, of Dalton's atomic theory. He did say atoms of different elements are different in some fundamental way, which is correct. So an atom of copper is different than an atom of iron in terms of protons and neutrons and stuff of that nature. Atoms or chemical compounds are always formed when atoms of different elements combine with one another. A compound always has the same relative number and types of atoms that occurs. And again, as we sort of saw in that last example I just did, if you have sort of compounds of the same elements but different amounts of them, they do sort of kind of come together in these kind of multiples of whole numbers of how they do come together to make these compounds. And chemical reactions really involve the rearrangement of atoms. Again, we do not really change, excuse me, we really do not change any elements along the way in a normal chemical reaction. You have to go to a nuclear reaction to actually change your chemicals. In a nuclear reaction, you do not have conservation of elements. Elements are changed into other elements, and that's really because they play with protons and neutrons. They play around with the nucleus, which is why anything involving like a nuclear reaction usually involves a lot of energy because you're playing around with like neutrons, protons, things in the nucleus. Normal chemical reactions, excuse me, are only playing around with those bonds, those electrons. So some can be pretty good in terms of energy, but in comparison of a chemical reaction to a nuclear reaction, the comparisons of energy is nowhere near each other. Nuclear is way more energy than your greatest sort of exothermic sort of chemical reaction that occurs. So atoms themselves, again, are not changed as a result of any type of chemical reaction. So again, that's sort of Dalton's atomic theory. You do need to know the parts of it. You need to know what's sort of not correct as well. So this question will help us understand what things are not correct still. So which of the following statements regarding Dalton's atomic theory are still believed to be true? Elements are made up of tiny particles called atoms. That is still believed to be made true or still believed true. Atoms of a given element are identical to each other. So as we just talked about, obviously isotopes means that is not so true anymore. A given compound always has the same relative numbers and types of atoms. That is true. And atoms are indestructible. That is also nuclear sort of chemistry. You can change an atom into something else or a different sort of atom, and they are not indestructible in that sense. Otherwise, we wouldn't be able to change. Start with like a uranium and end with like a plutonium type of element. So the two here off the list here that are still true are those guys. So you do need to know Dalton's atomic theory, the different parts. You need to know kind of which things are still true and which things obviously are not so considered, I would say truthful today or is true today. Any questions on that there? Yeah. So some other sort of laws and stuff, which we'll get to when we talk about gases. Guy Lucix, he measured under the same pressure and temperature conditions. You might have learned his law. His law, by the way, is P1 T1 equals P2 T2. It's Guy Lucix law. He basically saw that as the pressure sort of changed, so did the number of, or as the volumes of gases changed, so did the number of moles that are sort of reacting. Avogadro Also looked at volume and the number of moles of gases happening. Avogadro's law there, V1 N1 equals V2 N2, N being the number of moles, V being volume, obviously. And there's some sort of aspect of these things, as we'll talk about when we do get to sort of the gas chapter, that allows us to do certain types of calculations based on the idea of sort of what is going on. So we do have some laws, we do have some hypotheses going on here, and again, that sort of scientific method. I think we'll skip through this here. We'll revisit those guys when we do get to the gas chapter. So as we talked about, Dalton pictured, again, atoms as a combination of these elements. And again, you can see different combinations of elements will create different compounds. And again, the sort of ratio of, the mass of, say, in this case, nitrogen to oxygen, again, they would be related to each other by these sort of whole number ratios. Now, based on Dalton's atomic theory, there was this idea that the atom is defined as the basic unit of those elements that could come into chemical combination. A lot of experiments determined that although atoms are obviously extremely small, they actually do possess an internal structure. And that internal structure is where we have our subatomic particles. And those are the three that we just talked about there: electrons, which obviously are negatively charged. We have protons, which are positively charged. And we have electrons, which are negatively charged in this case. And we're going to go through certain experiments to sort of focus on some of these particles and sort of the idea of where they sort of end up in terms of the atom, and why in certain cases maybe they thought they're in different places in the atom versus where they sort of end up. So let's take a look at all these things here. So really the first major sort of exploration of the atom really began with CRT Thomson, and really he was looking at electrons. So he was really sort of exploring these electrons, which are negatively charged. And he did a lot of work with what I referred to as cathode ray tubes. And a lot of times they are referred to as CRT. You may be familiar with cathode ray tubes if you've ever seen like a really old sort of TV that has like a back on it, the picture tube in it, not like any of the modern TVs that we have. That is a cathode ray tube. If you ever seen pictures of an old computer monitors that have like the big back that comes out of it and stuff like that, obviously not flat screens or anything like that, those are also they used to call them CRT monitors years ago. Those are cathode ray tubes as well. And the idea of exploration of these particles which have charges were done with the idea of a really important concept in chemistry that we'll talk a lot about in different areas. And that's the idea of opposites attract. And that is also really electrostatic attraction. And the idea there that opposites attract is the idea that much like in life, two positive people probably don't want to be near each other. It's just like too much positivity happening, right? Two negative people don't want to be near each other. But right, they say you try to find somebody that balances you out, right? So you get like a positive, negative person that sort of balances each other out. And it's the same idea in chemistry. Things that have the same type of charge do not want to be near each other. They do everything they can to try to escape each other. In certain cases, they can't really escape each other. So they will continue to kind of even move around to try to find the best way or the most escaping that they can do. And that's what happens, for example, in bonding, intermolecular forces. When a bunch of molecules get together, there's always going to be sides of those molecules that really don't want to be near each other. And they'll keep moving, actually, to try to find an arrangement where, they're kind of semi-happy in terms of being close to things they want to be close to and keeping as much distance they can from things that have the same type of charge. Opposites will always attract each other. And that's the idea, for example, like ionic compounds. Those are metals and nonmetals. Metals lose electrons, become positively charged. Nonmetals become negatively charged. That is what holds together, for example, an ionic compound. Absolutely no sharing electrons happening there. It is the attractive force between the positively charged ion and the negatively charged ion that plops those things together and keeps them together. So the sort of advantage of a lot of these experiments outside perhaps the CRT tube is a lot of times they will use a lot of sort of radioactive sort of particles, and a lot of these sort of experiments used to explore the atom and try to figure out what's going on. And there's a few particles that's used a lot, alpha particles, and these are positively charged radioactive type particles. A lot of times people would use beta particles. These are negatively charged radioactive particles. And sometimes people would use gamma rays, which has really no charge. So you can kind of see that these sort of particles do sort of reflect the charges that we see in things like electrons, protons, and neutrons, and they're used a lot. So the other thing that they use a lot in a lot of these sort of experiments were things like electrical fields and magnetic fields. So for example, if I had an electrical field, like a positive sort of field there and a negative field happening, and I shot a particle and it kind of bent up towards the positive part of the electrical field, that would mean that that particle should have what type of charge? Yeah, it should have a negative charge, right? Opposites attract, so that's why it's going to bend towards the positive side of the electrical field. If you shot a particle and it bent towards the negative side, it would mean that it probably has a positive charge, right? Because it's going to kind of attract itself. Also, if you shot something through an electrical field and just kind of sailed right through, probably had, yeah, no charge, right? Because it's not going to be attracted to either one. So a lot of times, a lot of these experiments used to sort of explore the atom use things like electrical fields, magnetic fields to take advantage of these sort of charged radioactive particles. Also allows you to know what's going on inside the atom, right? Because how the atom reacts to things with charges heading at them will explain maybe what type of charges the atom has, right? So if you shoot something at an atom and it comes back at you, and you shot something that was positive and it just bounced right back at you, then probably a lot of the atom is positively charged, right? It had to hit something positive to make it bounce back at you. If you shot a particle and just went straight through it, it either didn't hit anything with a charge or hit empty space, right? So these are things and ways that they could explore what's going on with the atom through the use of these things. They also use a magnetic field, which has a south pole, north pole, kind of works the same idea, and it can also sort of bend particles with charges. So the first major sort of venture into understanding what's going on with a particle like an electron was done by Thomson. He did use the CRT tube, and what he was able to determine by doing experiments with these CRT tubes is he was able to determine the charge to mass ratio of an electron. And what a CRT tube looks like is something like this. It typically, again, has a positive side and negative side in the tube. It shoots negatively charged particles like electrons. So it's going to go away from the negative side of the tube. It's going to head towards the positive side of the tube. And a lot of times, for example, they'll put some type of fluorescent material up here, and you could actually visually see sort of where the beam is actually hitting when you look at it. And here's this, maybe. Guess so. Maybe. There you go.
A beam of electrons, as do television sets and computer monitors. A luminescent material has been painted on part of the inner surface of the tube. It produces light when electrons strike it. The electrons originate at the cathode of the tube. The long, thin object entering the scene is a bar magnet. The position of the bright spot on the screen can be changed by moving the magnet near the beam of electrons. This process is analogous to adjusting a television picture.
Yeah, so you can see obviously that beam has a charge as it's affected by the magnet, right? So again, this is how we could use those things. I know it's hard to believe that people used to call TV repairmen to their home to repair their TV. They take the back of the TV off, they fix the picture tube and stuff like that. I know. We didn't run just to Costco and try to fit the 82-inch TV in our car that's this small, right? Everybody sees that, everybody at Costco with the, I know, we just get rid of the TV box and try to squeeze just the TV in there. We've all done it. Super Bowl comes in February. We've all done it. It's all right. So there is Thomson. And like I said, the major finding of Thomson with his CRT tubes is that he was able to determine the mass or the charge to mass of an electron. And he determined it as this value here, minus 1.76 times 10 to the 8. Coulombs is a unit of electrical charge per gram. So coulombs charge to mass, which is grams of an electron. You don't necessarily have to know that number or anything like that, but you do need to know that Thomson did experiments to explore the electron with CRT tubes, and he was able to determine the charge to mass of an electron. Now, the next sort of major sort of step to understanding electrons was actually done by a guy named Millikan. And Millikan did what is referred to as the oil drop experiment, and it's pretty much what the name sort of sounds like. He had a chamber where he had an electrical field. He would shoot the oil in there and atomize it. And what would happen is you would have a drop of oil that would normally want it to just fall based on gravity. And as it falls, it's going to pick up a little bit of a charge. What he was actually able to do in his experiments was he was able to really sort of adjust the electrical field in such a way that basically the drop of oil just kind of hung there and then go up, then go down, just kind of just hung in place. And that was a major step to him understanding the charge of an electron. So we have Thomson, who did some work with CRT tubes, who was able to figure out the charge to mass of an electron. So the charge to mass of an electron was Thomson. Millikan was able to figure out the charge of an electron. And really the significance of both of those experiments together is from those experiments, you're really able to figure out what the mass of an electron is. Because frankly, if you take the charge of an electron and you divide it by the charge to mass of an electron, the charges will cancel and that will give you your mass of an electron at that point. So you need to know Millikan did the oil drop experiment. Here's sort of what that looked like, I think. Maybe. Let's see. Hit that one. So those are the oil droplets. And again, he was able to really sort of play with that electrical field. And again, just kind of keep that oil droplet suspended there. Obviously able to do some calculations. As you can see there, 1.6 times 10 to the minus 19 coulombs was the charge he associated with that. That obviously, along with our Thomson experiment, allowed us to really do the mass of an electron by doing that calculation. And it was determined that the mass of an electron is in the ballpark there of 9.09 times 10 to the minus 28 grams. Is that a large number or a small number? What is that? That's a pretty small number, right? That's like 27 places to the left and put a bunch of zeros in front of it. All right. So again, you need to know about Thomson, his experiment, what came out of it. You need to know about Millikan, his experiment, what came out of it, came out of the combination of both of those experiments together, which obviously is the mass of an electron, which does have that mass and obviously is negatively charged. So this leads us to the idea of, by the early 1900s, there really was this idea that the atom definitely contained electrons through these experiments and that they were electrically neutral. So clearly, if the atom contained electrons, which we know are negatively charged, and they are electrically neutral, which means they have no charge when it's all said and done, that does mean that they must contain something that is positively charged there to balance out the negative charge from the electrons. So around the turn of the last century, the accepted model was the one proposed by Thomson. It's actually a different Thomson than the J.J. Thomson. So it's a different Thomson. And what he said was the atom can be thought of as a uniform, positively charged sphere. So basically, you could think of the atom as a sphere, and we have all this positive charge spread out over this big sphere. So all that positive charge. And he said that the electrons were to be found embedded inside the atom, like raisins, in what is referred to as the Plum Pudding Model. And that is basically pudding with raisins in it, basically. So the pudding is like the smear of sort of positive charge. The raisins are like the electrons that are basically embedded in there. And one of the other major sort of points of the plum pudding model was that most of the mass of the atom was the electrons. So after sort of the early work on the atom, this was really sort of the basic idea and understanding of really what they thought the atom sort of looked like, was this plum pudding model. And obviously here a much prettier picture of what it looks like. And this was sort of the accepted model of the atom for a fairly good amount of time. But again, the idea of a model or a theory is something that obviously can be revisited. And it was really revisited and really kind of the next major step towards understanding the atom. And that really came with the gold foil experiment. And the gold foil experiment was done by Rutherford along with Geiger, like the Geiger counter for radioactivity, and Marston. And he used these alpha particles that we talked about. So those alpha particles, again, are those radioactive, positively charged particles to explore really the nature of the atom. And really what he sort of thought was going off of sort of the plum pudding model here. He was going off the idea here. He's going to shoot these alpha particles at pieces of gold and other metals. Obviously, the pieces of gold represent gold atoms, right? And things of that nature. So, what he imagined was because he was going to shoot these alpha particles at this sort of big jello pudding of positive charge, they're heavy, they're radioactive, they're really helium, they're moving really fast. They would expect it to kind of punch through, but with some deflection. So if you think about, like, for example, if you had like a piece of paper, right? And if you were to hold both sides of the paper really, really tight, right? And you were able to like shoot like a pin at it, right? Really tight. It's probably going to be able to pop through there, right? But it's probably going to kind of deflect a little as it tries to sort of pop through there. And that's really what they sort of expected to happen in that particular case. And they actually were quite surprised based on what they actually observed happen. And what they actually observed happen is, as you can see here,
Rutherford and his co-workers are studying the angle.
actually, we'll come back to him in just a second. What actually happened here is they saw that most of those alpha particles basically went through undeflected. So you can see here, this is sort of the setup. There's the screen, and most of those particles basically sailed right through with no problem. Now, every so often, what they observed was that these alpha particles basically bounced off at these really big angles. So these alpha particles bounce off at the big angles. They actually also sometimes head back to really the source of where they came from. So if we think about it here, about that, right? If I shoot an alpha particle, right, at my atom, and it pretty much doesn't hit anything, right? Why did it just go straight? There's nothing in its way, right? It didn't run into anything, right? Nothing is there to change its path. So that explains, why they saw, for example, most of the particles, went through no problem, because clearly that would mean it didn't actually hit anything, right? What would cause those alpha particles to bounce off at really, really large angles? It had to hit something very, what type of charge? Alpha particles are positively charged, so it has to hit something that's very, very positively charged, right? Opposites attract, things with the same charge repel each other. So this is really surprising because what they thought was like my positive charge is spread out all over the place, right? So every time you shoot a particle at it, it should hit something positive, right? So we should see some type of deflection that should happen. So this had them really rethinking sort of the model of the atom, that maybe the atom doesn't have all this positive charge basically spread out all over the place, but maybe the positive charge, instead of it being all over the place, if I take all my positive charge and I fold it, what do they say, it's like 7 times or something? You can't fold it anymore after that, I suppose, right? If I take all my positive charge and fold it like that into a very tightly dense positive core, right? And I shoot my particle at it, it comes back at me, right? It hits something very, very densely positive. So this is, again, what they sort of witnessed when they did this experiment, which is something very, very different than what they sort of thought about going into it, where we had all that positive charge. Let's go back and take a look at that.
In 1910, Rutherford and his co-workers were studying the angles at which alpha particles were scattered as they passed through a thin gold foil. Most of the alpha particles passed through undeflected. However, a few were found to be scattered at large angles, some even back in the direction from which they had come. This meant that they had collided with an object much more massive than the alpha particles themselves, yet so small that only a few alpha particles encountered them. This atomic level view shows what is happening. Most of the atom is occupied by the low mass electron. The nucleus is small and massive. When an alpha particle encounters a nucleus, it is scattered at a large angle.
So this was obviously a major sort of step forward into the understanding of really what's going on in terms of the atom. Again, they went into an experiment sort of thinking and hypothesizing, one thing's going to happen. And obviously is why we do experiments, right? We can find new things and discover new things through experimentation. And they were very, very shocked. Like I said before, they saw these alpha particles basically bouncing at these large angles every so often, coming back to the source. Again, like shooting a gun at a piece of paper and having it come back at you. And again, on the left is sort of what they envisioned happening. On the right, again, is sort of what we talked about did happen. Obviously, those guys that sailed through pretty much didn't run into anything to alter their course that much. So what this meant was that what we had to sort of do in terms of the previous model, which was our Plum Pudding model, is go, maybe not so right, and come up with really a sort of revised version of what the model of the atom is and sort of the model that we think of today. And he said that most of the atom is really empty space. And again, that's what accounts for all those alpha particles having no problem selling right through or anything like that. He said that atom has a dense center of positive core, which they call the nucleus. And obviously that would account for why we see those positively charged alpha particles bouncing off at large angles, as later experiments and stuff shown in our nucleus. That is where we have our positively charged protons, which is causing that positive core that we see there. Later on, found in like the 1930s, there's also neutrons hanging out there in the nucleus in the 1930s. A guy, again, by the name of Chadwick, as we'll talk a little bit about here, discovered neutrons. It wasn't, again, at the same time here as Rutherford. It was like in the 30s, 1930s they did. Electrons are actually traveling out from the nucleus at some distance. Electrons are traveling in that empty space, sometimes referred to as like the electron cloud as they're moving around. And another really major difference between the Plum Pudding model and really Rutherford's model of the nuclear atom is the idea that no, it is not the electrons that actually is most of the mass of the atom. it is actually the nucleus that contains protons and neutrons, again, later found in the 30s, that actually makes up most of the mass of the atom. So we basically have a nucleus where we have protons and neutrons. We have electrons traveling about the nucleus in the empty space. By the way, as we'll also talk about, and maybe you know, electrons do not travel in pretty circles. They travel randomly about that empty space in the nucleus. They don't travel in orbits or pretty circles or anything like that. They are randomly kind of moving around in that empty space. Any questions on that there? So here's this little table, kind of summarizes all the experiments we sort of talked about up until this point, and obviously the major things that sort of came out of it as well. So speaking of protons, again, were sort of discovered, and they're located there in the nucleus. They have a mass of 1.67252 times 10 to the minus 24 grams. If you remember, our friend the electron is like 909 times 10 to the minus 28 grams. Which one's heavier, the proton or the electron? It is the proton. Smaller negative exponent, bigger number, right? You're only doing like 24 places to the left or 23 to the left versus 27. So that is true. Protons are positively charged found in the nucleus, and they're about 1,840 times heavier than any electron that's flying around. So that again makes sense if you think about what Rutherford said. The nucleus makes up most of the mass of the atom, since in the nucleus, that's where you find protons, which are like 1,800 times heavier than any electron that's kind of flying around. So again, that all sort of matches up. At this stage, scientists sort of perceive the atom as follows. The nucleus is basically most of the mass of the atom. When you think of the atom, you can think of it like the size of the Superdome. If you've ever been there, I hear they just remodeled it because they got the Super Bowl this year, I think. So they actually put a bunch of money into it. But years ago when I was there, it was not remodeled very much. But if you've ever been to the Superdome, it's a very big place. Even if you're sitting on the top, even when you're sitting in your seats, you feel like you're falling. It's so tilted, and there's so many seats and stuff like that. It's fun when you try to get up to get out. You're like, whoa, I'm gonna fall. But the Superdome, or a big stadium, and like the nucleus is like a small marble, and like the 50-yard line in the middle of it is sort of the idea there. Lots of empty space, lots of place for those electrons to fly around in. But again, the sort of mass of the atom is made up of that really small sort of marble on the 50-yard line. Is there an attraction between electrons and the nucleus? Should there be an attraction between electrons and nucleus? What do you think? There should be, right? Electrons are negatively charged, right? Nucleus is basically positively charged, so there is an attraction, which is why electrons just don't sell off, right? They're kind of tied to that attraction. Some tied a lot stronger than others, which, as we'll talk about when we talk about bonding, why only certain electrons are involved in bonding and other ones aren't, depending on how close they are to the nucleus. They're kind of tied down, they can't really leave. Other ones can, under the right sort of circumstances, kind of pry themselves away from the nucleus. There was believed for a very long time that in addition to the proton in the nucleus, that there was another sort of subatomic particle found in the nucleus. And it wasn't really until 1932, a guy named Chadwick did a lot of work with beryllium. And what he noticed was it would sort of emit particles or rays that were very similar to gamma rays that had no charge. And it was later found and named that these particles are what are referred to as neutrons, which do not have a charge. But they did find that the mass of a neutron is 1.67495 times 10 to the minus 24. We go out those far decimal places, that tells us actually the neutron slightly edges out the proton in terms of being the heaviest. So when we talk about neutrons, protons, and electrons, these are the heaviest, with the neutron being the heaviest of all of those, the electron being the lightest. And this also sort of puts into perspective the idea that the nucleus is made up most of the mass of the atom, because within the nucleus you have protons, which are about 1,840 times heavier than an electron, and you have neutrons, which are also about 1,840 times heavier than any electron. So that combination, having basically your two heaviest particles within the nucleus, is why the nucleus is making up most of the mass of the atom, because again, each of those individually are about 1,800 times heavier than any electron that's flying around. Any questions on that there? And here again is the comparison of the masses. Again, the neutron just barely edging out the proton, and the electron much, much lighter than either of those two and their locations, right? So again, you do need to know where you find these particles, electrons in that empty space flying around, protons, neutrons found in the nucleus. You do need to know, just to summarize in terms of the atom, I got a picture here. So here's sort of what the atom looks like. That again, pink area is that empty space. It's really the electron density map. Electrons are moving around randomly in there, and you can see a very, very small little nucleus there, but very massive in terms of the nucleus. Now, you do need to know, as I mentioned, you do need to know what the Plum Pudding Model is, yes, and the different parts of it. You do need to know Rutherford's gold foil experiment, what he did, what he expected to happen, what actually happened, and how that changed the model of the atom, which means you clearly also need to know the model of the atom as well. You need to know where protons, electrons, and neutrons are found, their charges, and you need to know which one is the heaviest and which one is the lightest. You don't have to know the exact numbers of those things, but you just need to know sort of their masses, in that sense, the order. Any questions on the atom and how we got there? All right, we'll wrap that up for today.